Hey everybody, great to be here. I'm Ariel Ekblaw, and I'm going to talk to you today about the different ways that AI is intersecting with space infrastructure. Three key ways to think about it. We can use AI embedded into hardware models to self-assemble really grand-scale infrastructure that's bigger than our biggest rocket payload fairings. So that's going to be a big focus of this talk, is in-space self-assembly. The second, of course, a lot of people have probably heard about AI data centers in space. So we may also use space infrastructure to create the compute support for AI. And then things that you're actually doing when you're in microgravity can sometimes be combined with AI models in a really interesting way. And so I'll talk to you a little bit about the promise of microgravity bioscience. But the first thing I want to call out is that this is the current state of the field of space architecture. Really amazing, some incredible feats of human engineering, but they're always axial. They're aluminum tin cans, basically, pressure cylinders, in X, Y, Z Cartesian coordinate planes. And I think instead, in space, we should be building radially with spherical coordinates. We could be doing things so much bigger than just the kind of size and shape of the rocket payload fairing. So my question in my work from MIT PhD to now is how would we achieve something like this, a ring world? This is an image out of Neil Stephenson's Seven Eves. This is probably not going to be how we do it. This is how we have built space infrastructure for the last 20 years. Humans in extravehicular activity suits, EVA suits, basically building some of the most sophisticated technology known to humankind by hand in orbit. Instead of this paradigm, could we do something more akin to self-assembly in biology, where there's a certain intelligence embedded within each unit that allows growth, indeterminate growth over time, but then still a logic to the overall superstructure that is useful for logistics and planning and pragmatic use. So this model of self-assembly inspired what I call tesserae, which are basically space Legos. So what you see here is basically our product roadmap now that we work on inside of Ariel Institute, which is my nonprofit. We build sophisticated individual tiles that have a lot of sensing on board. I would have just called it machine learning a few years ago. Now we think about it in kind of like a broader AI-enabled sense for this hardware. Visual sensors on the sides, the ability to autonomously float in orbit and use really special electropermanent magnets to be drawn together to dock. So again, we're actually using a principle of self-assembly in nature where certain forces are dominating over gravity, like electrostatics at a certain level, or like Brownian motion. And when you're floating in free fall around a planet, you have this kind of amazing opportunity to bring really large items to float together and dock and interact. So that's the mechanism behind some of this work. We are trying to build different geometries. I was incredibly inspired by Bucky Fuller, so our first geometry that we're targeting is a buckyball, 20 pentagons, 12 hexagons, glorified soccer ball in orbit. And then from there, we are excited to stack infrastructure like this into a big space station. We have built a human-scale architectural model that's 25 feet in diameter. That's this space habitat pavilion. It sadly does not self-assemble. We have to build it on the ground, but it's around if you ever want to come to Boston and see the inside of future space habitation. This is an example of the tiles on the International Space Station having self-assembled. You're looking at the cupola down to Earth. To give you a sense of the iterative engineering process that goes behind this kind of work, it's a lot of zero-gravity flights. Has anybody here been on a zero-G flight? Affectionately amazing, Esther, affectionately known as the vomit comet, because it does what you want a plane never to do, pitches really steeply upwards, noses over, points towards the ground at 45 degrees, basically flies that parabolic arc 30 to 40 times in the sky. I've now done this 14 times myself. We bring 25 to 50 people every year onto these flights to do their own research. This is a very genuine offer to the Foresight community. If you have an idea for a project you'd like to do in zero-G, hit me up. We'd love to collaborate and bring you on one of these flights. We've tested with Blue Origin, suborbital. We've done 2 missions to the International Space Station, and we're actually queuing up the Gen 5 tiles to go to the ISS again next year. So now I'm going to quickly pivot into Why would you care about building big things in space if you don't otherwise love science fiction? I, of course, love science fiction, so it's a big draw, but what pragmatically could we do with this kind of infrastructure? The International Space Station is about to be decommissioned. We're about to lose it. It means it's really urgent to be able to build and replace volume for research on orbit. We are looking at things like organoids that behave differently in zero-G, tissue engineering for things like artificial retinas that would cure macular degeneration and retinitis pigmentosa that are uniquely well fabricated when they're floating, getting a really high quality protein matrix. These are the types of things that we envision enabling within a larger volume orbital biolab. Probably not the first person to tell you that the cost to get to space is dropping so dramatically that it's finally feasible to think about this. This is where that application of AI again comes in, AI plus bio. Thinking about getting data that you can only get when you're floating in space for your biological samples, feeding that into interesting AI protein folding models, I think will really advance the state of AI. And it is now basically like FedEx costs to get to space. It's remarkable. In 15 years, it's dropped from $50,000 a kilogram now to about $200 a kilogram, with SpaceX, Starship, and New Glenn coming online. So if you can ship cargo around the world, you can ship it to space. Not the humans, we're a little bit more fragile, we're still a little bit more expensive, but we're working on that as well. So really amazing opportunity. It's time to build. We'd love to have ideas from this community about what we do in space. I'll just leave you with this final thought. That's my own timer to keep myself honest, Allison, for 7 minutes. This was a design for Newton's cenotaph. Long after he died, Edward Boulay in the late 1800s wanted to build a 150-meter span dome to honor Newton. Those tiny little things at the bottom are the humans. This can't be built on Earth, even really with modern technology. This is the kind of monument that we could uniquely build in space. And so I do think that the field of space architecture is something where we can begin to think in grand visions for humanity about what's capable, what we're capable of, what's possible. And so we're really excited to be at what we think is the forefront of this future. Thank you so much.
Very cool. Thank you for the presentation. Looking at your dome, I'm wondering, are you all working with Josh Simons on the work he's doing with NASA on glass moon habitats made in situ?
I know of the ISRU things to do glass. I have predominantly been focused on microgravity, so not on the surface, but that is a great reminder. I don't know his name by name, but I'll look into that work. We'd love to connect with you after.
Sounds good. Thanks.
Thank you.
Thank you for that inspiring talk. My question has to do with, certainly I'm concerned about what we are doing in space in the US, but
with space debris.
I think what we also have to think about is what others are doing in space, so especially China. And my understanding now is that we don't have the technology to have eyes on what they're doing. And so I'm wondering if there's another way to think about that, and because I think it's another consideration. If these costs have gone down, then that's obviously, another player out there that can do a lot, and how do we stay ahead of that curve?
Yes, so I think you're hitting on a really important trend in the space industry, which is we have a very explicit, very intense Cold War space race with China. They basically replaced the Russians as our primary adversary in that domain. There's a lot of activity that civilians don't hear about. There are crewed things in space that are not just the International Space Station and NASA. China has famously landed on the backside of the moon, has their own space station, smaller but very interesting and advanced, Tiangong. So I do think it's worth having capability to try to work peacefully as long as possible. What would be really interesting and doesn't exist today is a way for me as a scientist at MIT or in my capacity at Ariel Institute to have any positive aspirational collaboration with the Chinese. Even in the heart of the Cold War, we worked with the Russians in the space program. It was a point of diplomacy. We did the Apollo-Soyuz interface testing. China's space station, space agency is military only. There is no civilian counterpart to NASA in China, and so it's really hard for us with ITAR and export control to work with them. So if that dynamic shifted, we might be able to find some points of collaboration. But yes, for now, there's a huge focus on getting better intel and space-based work through NRO and DoD to keep track of what the Chinese are doing. I would say I think U.S. military has a pretty good set of eyes on it, but certainly in civilian world, we don't as much. Thank you very much.
Okay. Thank you very much for the talk. Very, very inspiring. I was curious, what do you think the biggest technological breakthrough needed to actually make this happen? Is it materials? Is it robotics in space? What do you think is the pain point to make this happen?
Great question. For my passion application of having this be a useful habitat system, we've already done all the innovations we need on the electromechanical side. We know that they can dock, we can seal them. We have a certain sense from material science of how big we can make an individual panel before it buckles. The real limitation for me is how far could we take this away from Earth, outside of the Van Allen radiation belts, and still have humans live in it long duration and be safe and not die in an accelerated way because of radiation. Even the trip that Elon wants to take from Earth to Mars will be a significant radiation load. And so thinking about the ways to do water walls or a carbon boron nanotube, encasing, there's some early work at MIT looking into that. That's one of the biggest open questions for human spaceflight, is how to solve the radiation challenge. We're lucky that we're planning to operate this biolab at the same altitude of the International Space Station, so we're protected still by Earth's magnetosphere, so we're not going to have as much radiation load as you'd have on the moon, for example. Yes.
Thank you so much.
Thank you.